Hi guys, I'm Josh, and this is Computation in C, a set of talks for beginners who want to form a foundation for understanding computers, programming, and the history, math, art, and science of electrical computation. In the last few talks, I've been trying to take you up to the modern time of the beginning of computers, where they came from. I'll show you here. We started all the way back right here in the Enlightenment with John Napier and the invention of logarithms to speed up computation processes. And as we discussed, as we get into the Industrial Revolution, the maths become so incredibly important for calculations and understanding how this new industrial world is working, that scientists and people that were studying and working on all the different maths that would run the Industrial Revolution, they needed ways to do computation faster. So John Napier's logarithms became a part of how everybody did their work. Slide rules were an important tool that were used to speed up calculations. And all of these things, all the way up through Charles Babbage's difference engine here in the early 19th century, were all mechanical tools that helped scientists and thinkers run calculations more accurately and more quickly. I'm talking about the maths here when I say calculations. Well, as we discussed, right here, 1831, Michael Faraday invents the dynamo and the electrical revolution begins. And we see the invention of the telegraph, the telephone, and air flight, all here at the end of the 19th century and early 20th century. And all of these new inventions, plus the existence of electricity, are really accelerating our capabilities as mankind, and the ability and the need to do calculations more rapidly is becoming more urgent. We discussed that initially computers were running and were storing information. Electrical computers were storing information using these vacuum tubes. And then eventually, some more pictures here of what these early computers that used vacuum tubes looked like. They were huge. And then we come along for the creation of the transistor, which happened, I recorded to you in one of our last videos, right around 1947. And really the computer revolution takes off, because now we have an invention that allows us to store information using electricity without taking up a lot of space. So here we are now. I've spent a lot of energy talking to you about how did computers come to be? How did we think about computation up until the existence of computers? And now here we are. We've got the electrical computer. We've got the transistor. And I want to spend some time today talking more about how are we actually storing information and doing operations, computations using electricity. How is this happening? And in order to dive deeper into this, how does computer memory, how is it being used? How are we actually working with these things? We need to spend some more time on a topic that we started last time, which was, how do computers represent numbers? And today we're going to dive in more deeply into this topic by discussing the binary number system. So I was showing you last time the idea that if you had transistors that could be turned on and off, and you had three transistors side by side, how you could represent the numbers 0 to 7. So we're going to pick up here and talk more about how computers work with numbers and letters. So let's get started. So it was about 1703 when a guy named Gottfried Leibniz was credited with the invention of the binary number system. Let's take a second and look at this dude. Here's Gottfried. So Gottfried was born into a German family. He got a great education, and he rubbed elbows with some of the great thinkers of his time. It turns out this guy is independently known as one of the co-discoverers of differential and integral calculus. We also credit Isaac Newton with making that discovery, but these two guys independently made these discoveries of the calculus. But that's not all this guy is credited with. He's also credited with some of the first writing about the binary number system. Now, the binary number system is a system of representing numbers and doing operations on numbers like addition, subtraction, multiplication. But the numbers only have two symbols, 0 and 1. That's why we call it binary. Bi means two things, so it's a binary number system. So we're going to spend some time talking about his discovery and his writings about the binary number system, and how, even though there wasn't really any strong use for this number system, he wrote a paper called Explication de l'arithmétique binaire. He wrote it in French, and that became an important part of the historical record of the invention of binary. It actually turns out, most historians think, a guy named Thomas Harriot, actually 100 years earlier, had already discovered the binary number system. He never really published anything about it because he didn't see any use for it. So let's get stuck in. So first of all, I want us to think a little bit about number systems and counting. So first of all of us have seen what I would consider to be the simplest possible way to count. And that is to say, I only have a single symbol, and that is a tick mark. And when I put one tick mark, that represents 1. If I put 2 tick marks, that represents 2. 3, 4, 5. So this is a very simple method for counting up to 5, and then I can say 5, 6, 7, 8, 9, 10. So every time I want to represent a greater number, I have to add a symbol to what I've written. This works. It's pretty inefficient, but I think, as you all know, we began to move in the 7th century primarily to a base 10 number system using the symbols 0, 1, 2, all the way up to the number 9. So there were 10 symbols now that could be used to represent numbers. And this system allows us to represent numbers in a more compact way. Instead of representing 10 like this, I can represent 10 like this with just 2 symbols. So you've all learned, of course, this base 10 number system, but the point is we could have a number system using any number of symbols. And one of the other kinds of number systems we could have is the binary number system. It turns out this number system is so important for computers, even though it was sort of discovered and described long before computers ever came into existence, because in the world of electrical computation, we only have 2 states that can exist in the electrical circuitry. Either electricity is present or electricity is absent. We only have these 2 states. So we have to figure out how to represent numbers using just 2 states. And 0 and 1 become a simple way to talk about these states: the presence of electricity, the absence of electricity. So what we want to do today is just get familiar with how binary number systems work, because everything in computing is working on a binary number system. So here we go. So first of all, let's talk a bit about binary numbers. All number systems that we use here, all the based number systems, are positional. It means if I write the number 1 2, the number 12, this 2 means something different than this 1 means because of the position I've put it in the number. Let me give you another example that maybe is even more clear. If I write 2, 2, the number 22, this number does not mean the same thing as this number. How do we describe what it means? Well, you may not be incredibly familiar with this, but you might have heard your teacher call this the ones place, the ones position, and this is called the tens position or the tens position. Okay, that's kind of a simple way to talk about the positions, but let's examine what exactly do the positions mean. It turns out that what the positions mean are, in this first slot, I am discussing a power of 10 raised to the 0. What is 10 raised to the 0? Well, I think you all know 10 raised to the 0 is 1. In this position, I'm talking about a quantity of 10 raised to the 1. What is 10 raised to the 1? It's 10. So when I write the number 2, 2, what I'm really saying is 2 multiplied by 10 to the 0 plus 2 multiplied by 10 to the 1. And if I work this out, I get 2 times 1 plus 2 times 10. If I continue working this out, 2 times 1 is 2 plus 2 times 10 is 20, and 2 plus 20 is 22. So what I'm trying to drive home to you is there is a positional concept in your base 10 number system where you put the number in the digits indicates what power of 10 you are talking about. Okay? That's kind of how our base 10 number system works. So let's think now about how the binary system works. So when I represent a number in binary, let's come over here. When I represent a number in binary, I'm just going to make a number up. 1, 0, 1. Okay? 1, 0, 1. What I'm actually saying is, I take the first position, that is 1 times 2 to the 0, because this is a binary number system. We only have 2 possible numbers, so everything is in a base of 2. 1 times 2 to the 0, 0 times 2 to the 1, 1 times 2 to the second power. And if I add all these up, well, what do I get? 1 times 1 is 1, 0 times anything is 0, 1 times 2 to the second power is 4. So when I add up, I'm using decimal arithmetic here because I know you're familiar with it. So when I convert these into decimal, I'm going to get the number 5. So 101 represents the number 5. Now let me just bring you back to my example that I gave you earlier. Okay, what did I say that on, off, on of a transistor would represent? I'd said, well, let's say that represents a 5. So you see here in this concept of an electrical transistor being on or off, I could represent 1, 0, 1, which is the number 5. And I'm kind of giving you the math of how I arrived at the idea that 1, 0, 1 would represent the number 5 as we know it. So it's representing 5 things. All right, so this is how the binary system works. What I want to do is spend a minute discussing, you can see here how I can take any binary number and convert it into a decimal number. I just take each of the positions and I multiply them by the power of 2 that the position represents, and I can come up with a decimal number that's represented. How do I come up with a binary number if I have a decimal number in front of me? How do I do that? So let's look at another example that I want to show you, and that is, let's say I have the number 12, the decimal number 12, and I don't know, how would I represent that in binary? Let me show you a mathematical procedure that will perform this transformation for you. So we're going to divide by 2. That's the method, divide by 2. So the first thing I'm going to do is say, what is 12 divided by 2? Okay, 12 divided by 2 equals 6 with a remainder of 0. There's no remainder when I divide 12 by 2. All right, let's take the result here. 6 divided by 2 equals 3. Again, there is no remainder when I divide 6 by 2. Let's keep going. 3. When I divide 3 by 2, it equals 1 with a remainder of 1. Okay? 1 with a remainder of 1. Now we're still not done yet. We're now at the number 1. What happens when I divide 1 by 2? Well, 1 will not divide into 2, so I get 0 with a remainder of 1. So if I take any number, any decimal number, and I perform this technique, I divide by 2, I take the result, I divide by 2, I take the result, I divide by 2, until I get to 0, okay? That 2 will not go into the number anymore, okay? For every operation, I notate the remainder, okay? We have now produced the number in binary from the least significant bit, or the least significant digit, the least significant precision, to the most significant bit, the most significant precision. And so when I want to write this number, I'm going to write it from bottom to top. I represent 12 as 1, 1, 0, 0. This is the number 12. Now, let's just prove it to ourselves really quickly using this technique that I gave you up here. So let's take 1, 1, 0, 0 and convert it back into a decimal using the powers of 2 technique. So the way it works is I take the least significant symbol and I say 0 times 2 to the 0, 0 times 2 to the 1, 1 times 2 to the 2, 1 times 2 to the 3. Let's work out what these numbers are. Okay, so 0 times anything is 0. 1 times 2 to the 2 is 4. 1 times 2 to the third is 8, because 2 times 2 times 2 is 8. And when I add all these numbers up, I end up with 12. So we're right back where we started. So what I've just demonstrated to you is any number that you can represent in a base 10 number system, the number system you're familiar with, any number can also be represented in binary, and you can discover the binary representation using this technique of dividing the base 10 number by 2 and noting the remainders. Okay? Similarly, any binary number can be converted into a decimal number using the powers of 2 operation. So here we are now. I've taught you how to convert in and out of binary. Pretty simple. Let me teach you about some of the basic mathematical operations of binary. And the purpose of doing this is just to give you a comfort level that you believe math can be done on these numbers, and it's really very similar to the math you already know how to do. I'm going to focus on addition and subtraction. Multiplication and division have a technique as well. I'm just not going to go over them because I want to control the length of this talk. So let's take a look. I want to do arithmetic on the number 7 plus 3. So we know in decimal that equals 10. So I'm not going to run through the process of converting 7 and 3 into binary, okay? I'm just going to go ahead and tell you that the number 7 is 1, 1, 1, and the number 3 is 0, 1, 1. It would be a great exercise if you want to pause the video right now and run through the divide by 2 technique and just prove to yourself that's true. It's true. Now, let's take these two numbers, and I'm going to teach you how to add them. There are just a couple rules that you need to learn, okay? In binary, 0 plus 0 equals 0. Pretty easy. 1 plus 0 equals 1. Obviously, 0 plus 1 equals 1. I don't need to explain that, but that's also true. Okay, now here's the slightly tricky part. 1 plus 1 equals 1, 0. Because when I've already told you, the positional system only has 2 values, 0 and 1. So if I put 2 1s together, I don't have a way to represent that with just a single figure. I now have to use 2 figures. I have to use a 1 and a 0 to represent 1 plus 1, because there is no way to represent 2 in a single number. In binary, I need to use 2. So this is what I want you to keep in mind as we run through this operation. So 1 plus 1 is 1, 0. So what I'm going to do is, just like I would do in decimal math, I'm going to put a 0 in this position, and I'm going to carry a 1 into the next position, carrying a 1 over, because I can't represent it here. So now 1 plus 1 equals 1, 0, but now I'm going to add that extra 1, and so it's going to be like 1, 0 plus 1. The answer is 1, 1. The 0 is going to become a 1. So now I'm going to write a 1, carry that additional 1 again. What is 1 and 1? Again, we've already said it's 1, 0. So I'm going to write this as 1, 0. And here I've come up with the answer. 1, 0, 1, 0 is 10. Real quick, let's just prove that to ourselves. 0 times 2 to the 0, 1 times 2 to the 1, 0 times 2 to the 2, 1 times 2 to the 3 equals 0, 2, 0, 8. What is 2 plus 8? Well, it's 10. So I hope I've convinced you that by using this technique of 0 plus 0 equals 0, 1 plus 0 equals 1, 1 plus 1 equals 1, 0, you see how, as I'm adding, when I have an overflow in a column, meaning the sum of these two numbers represents a number that cannot be represented in solely this position, I have to carry the 1 over and bring it into this position, just like in the base 10 positional system. All right, one more example. Let's do subtraction. And I want to give you a really good example here of subtraction. So I'm going to give you the number 4 minus 1. 4 minus 1. All right. So how do I represent 4? I represent 4 as 1, 0, 0. Again, I'm not going to prove that to you, but that's it. Okay, how do I represent a 1? It is represented as 0, 0, 1. All right. And I want to do this subtraction. Obviously, I'm expecting the answer to be 3. So what are the rules for subtraction of these numbers? Okay, the rules for subtraction go like this. 0 minus 0 is, not surprisingly, 0. 1 minus 0 is 1. 1 minus 1 is 0. And now here's the tricky part. 0 minus 1 equals, you can't really subtract 1 from 0, can you? If you have nothing and you subtract one thing from it, it doesn't work. So here's the special rule you need to understand. 1, 0 minus 1 equals 1. 1, 0 minus 1 equals 1. And now we're going to watch how this actually works out in this math problem. So when I want to say 0 minus 1, I'm stuck. I can't do a 0 minus 1. So I need to do exactly like I do in decimal math. I'm going to be borrowing from the other positions. So I can't borrow anything from 0. There's nothing there. So I have to come all the way over to this column and borrow. So when I borrow this 1, what happens is this 1 becomes a 0. This 0 becomes a 1, 0. Okay? Now I want to borrow to turn this into something other than a 0. So I'm going to borrow from here. When I subtract 1, 0, when I subtract 1 from 1, 0, what do I get? I get a 1. So this now becomes a 1. And this becomes a 1, 0. When I borrow a number from the previous column, I just put it in front of the existing number in the current column, just like you do in base 10 math. So now let's do the operation now that we've borrowed everything the way we need to. 10 minus 1, or sorry, it's not 10. 1, 0 minus 1 is 1, just like our rule says. 1 minus 0 is 1. 0 minus 0 is 0. So I end up with 0, 1, 1. Is that number 3? Let's check ourselves. 1 times 2 to the 0, 1 times 2 to the 1, 0 times 2 to the 2. This equals 1, this equals 2, this equals 0, and we end up with 3. Okay, so we're not going to go over multiplication and division. There are rules for multiplication and division, and they work just the same. What I wanted to focus you on instead is just, hey, there is a method. There exists a method to do addition, subtraction, multiplication, division on these binary numbers. So here we are. I've proven to you that if I just had an electrical system that could represent two states, electricity is present, electricity is absent, I can start to represent numbers, and I can add them, I can subtract them. This is getting incredible. This was basically the invention of Gottfried Leibniz. He sort of discovered this number system, this binary number system, long before computers ever existed. It's a really fascinating story to read about him and like what was he trying to do. He was really looking for a unifying theory to unify like Aristotelian logic with modern day concepts and with his belief in God, and he was looking for a system to represent logical principles. It had nothing to do with computers. Turns out wildly useful when we move to computers. So let's wrap up here with a couple pieces of information about computer lingo and norms in the computing world. So I've told you now how the binary number system works. So, in the computer world, a single unit of information, a single binary digit, they're not digits, a single binary positional representation is called a bit. So we have a 1 or a 0, a single 1 or a 0 equals a bit, a single transistor, a single unit of information. If I combine 8 of these together, so 8 bits is what is called a byte. And this is important because in the computer world, bytes become an important concept. So 8 bits is a byte. You've heard people say, my hard drive stores 250 gigabytes of information. We're referring to the byte. So 8 bits in a row is a byte. You might ask yourself, and we're going to get into an important topic about representing the alphabet, why 8? Why did we say 8 bits is a byte? Why in the world did we say that? Well, early on in computing, in fact, right around 1963, so we're not far along into the computer revolution, the people working on this equipment realized, hey, we need a good standard for representing the letters of human languages. I've showed you how we can represent numbers, but how can I represent a letter? Well, it's really pretty simple. You just need to assign a numerical value to each letter. And then you can just say, hey, I'm going to say that this represents the letter A, this represents the letter B. So let's think for a minute, how many different unique numbers would I need to represent the alphabet you're familiar with? Okay, so let's just take a look. If I represent the letters A through Z, we all know that's 26 letters in the alphabet. Okay? Now, keep in mind, though, I want to be able to represent lowercase letters and uppercase letters. So if I want to say a letter's uppercase, well, I need symbols, or I need numbers to represent capital A through capital Z as well. That's another 26 unique numbers that I'm going to need. What else do I need to represent? Well, I need to represent punctuation marks. So things like the period, the comma, the colon, the question mark, these symbols that are very common in human languages. I don't know off the top of my head, but let's just say there's another 20 of those. Okay. What else do we need to represent in human language besides all of these sort of symbols? I think another thing that you might not be thinking of is I need to represent the numbers as well. So the numbers 0 through 9, that is another 10 things that I need to be able to represent. You might say, okay, wait a minute, I thought you already told me how to represent the numbers. Well, when somebody types a number and is writing a number in English language, it's different than writing that number and wanting to use it as a computation. It's a little hard to understand that, but let's just say it was necessary when they were describing the standard for how to represent letters to also include the numbers, which get included in written language as well. Okay, so let's just add all this up for giggles, and what do I end up with? I end up with 1, 2, 3, 4, 5, 6, 7 plus 12 is 82 different distinct values. Just to represent what we would consider to be common in the English language. Well, let's think for a second about other languages. If you're familiar with other languages, a lot of times a letter in another language needs to have an accent mark over the top of it. Or it needs to have, as in Spanish, a tilde over the top of it, right? So now we're looking at, we may have to re-represent the entire alphabet, okay, in capital and lowercase, just with the ability to stick an accent mark or a tilde over the top of the letter. And just to put that in perspective, this isn't exactly true, but let's assume we needed to do every single letter. That's another 52 symbols just by adding all these different accent marks that happen in other popular Western European languages like French and Spanish. All right, I'm going to end up with 134. Okay, so we're trucking along where, you know, we need a lot of different numbers to represent the popular languages. Well, it turns out that the most popular standard was developed in 1987. It's called ISO 8859. ISO, that stands for the International Standards Organization, and this is the 8859 standard for representing Western European languages, and in this standard they needed 191, so obviously there's even more symbols than what I've come up with here, but they needed 191 symbols to cover the majority of the Western European languages, including English. So this number, the question is, how many binary positions do I need so that I have 191 unique numbers? Okay, a little bit more math here for you, which we didn't talk about before. When I take 3 binary positions, 1, 1, 1, what is the number, how many unique numbers can I represent with this? I've shown you in my previous example, I can do 8 numbers. I can do 0 to 7. Okay? How could I have known that? Well, if I just say I have 3 positions, what is 2 to the power of 3? It's 8. That's how many unique numbers I can represent with 3 positions. Okay? Now, come down. How many unique numbers can I represent if I have 4 positions? If I have 5 positions, we can see here this. If I have 4 positions, I can get all the way up to 16. If I have 5 positions, I'm not going to do all these maths in my head, but the important one is if I have 8 positions, I can get 256 unique numbers. I can go from 0 to 255 with just 8 binary digits. And that's how, you know, this, if let me just prove this other part to you. I don't actually know the number off the top of my head. So what is 2 raised to the 7? Sorry, 2 raised to the 7 is 128. So 2 to the 7th power is 128. I'm doing this to make a point. Well, if the standard said I need 191 unique values to represent the Western European languages, but 2 to the 7 only gives me 128 unique values, okay, I need 8 positions. I need 8 positions to represent the popular human languages in binary. And so these 8 positions became the standard for what we call a byte. Okay, 8 bits is a byte. So this is what I wanted to help you understand in today's lesson. How does the binary number system work? How do we do maths? How did the binary system get used to represent letters and human writing? And I've described to you the original standard was called ASCII. That was 1963. But the more popular standard is the ISO standard, which became defined in 1987. So pretty early on in the computer history, in the history of modern computers. So we have A bit is a single, 1 or 0. A byte is 8 of them. We say that most computers are addressable by the byte. And what that means is if you have memory in a computer, let's take a look at some memory. So here we are looking at what you would recognize as a common memory chip. The way this device works, roughly, is each of these little contacts that you see here, each of these little metal pins, can be used to create an address. And an address is like telling the memory, look, memory card, I know you have a bunch of 8-bit areas, 8-bit banks of transistors. And I want to find out what is the value stored in a particular 8-bit stretch of transistors in 1 byte. I give the memory a number. I say, hey, go get me the value that is stored at this address. And the memory device returns to me, this is the set of 1s and 0s that are stored in the 8 bits that have the following address. So just talking about an address, you probably are thinking, gosh, that sounds really funny, Josh. What are you talking about, an address? All I really want you to think about is inside of a piece of memory, I have a bunch of different 8-bit strings of transistors. And they're all lined up together in a big, long, practically and definitely a microscopic device where there are banks of transistors that can hold 1s and 0s, and they're in groups of 8. And if I want to ask the memory device, hey, what's stored in this little block? I give it an address. I'm just going to make this up right now and say the address of this one is 0000. Okay? Now, if my addresses are only 4 positions large, I can only represent 2 to the 4th power, which is 2 times 2 is 4, times 2 is 8, times 2 is 16. I can only represent 16 bytes. So that's not nearly big enough to be an address in a real computer. But let's just assume here that I'm dealing with a 16-byte memory. There's 16 bytes of memory. The second byte of memory would have the address 0001. The next byte would have the address 0010. The next byte would have 0011. So if I went to the memory chip and I put a signal on the memory chip and I said, hey, go get me the value that's stored in address 001, it would faithfully take the values of those transistors and show me which ones are on, which ones are off. And this is how basically storage of binary information in computers functions. There is a physical device that has the ability to hold electrical charges that represent 0s and 1s. Those are literally a bunch of different little physical areas on this microscopic memory card, and each little area has an address. And I say, I want the number that's in this address, and I get it back. So in our next video, we'll start talking a little more about actually using a programming language to manipulate numbers. And I wanted you to really have this great foundation in where did computing come from? Where did this whole 1s and 0s concept come from? And really get firm in your head, I can use 1s and 0s to represent numbers, perform addition, subtraction, multiplication, and division, and we have now a system that I've shown you for representing letters and human language as well. So in our next video, we're going to start opening up our code browser and writing some real code. Thank you so much for being here. We'll see you next time.